Okay, hi everyone. So today we want to talk about inversion, and the idea is the following. That is, if you so let's define what an inversion is. Okay, so basically, inversion is actually a transformation with respect to a given circle. Okay, so what you have is the following. So let's draw a circle. You draw a circle in the plane. Okay, now the circle has center O and its radius is, let's say, k. Okay, we will call this circle C. Okay, so let's denote this by circle C, O comma k. Okay, so let's denote, so we have a circle C here with center O, radius k. Now what we can do is we can do a transformation, okay, of the plane. So pick any point P in the plane. So let's pick any point. Okay, not really any point, but pick any point P except one. Okay, except the center O. Okay, pick any point P other than O in the plane. Okay. Now what you do is you join the point O to the point P and make a ray. Okay, join O and P to get a ray OP. Okay, now what you do is you construct a new point P dash, okay, on this ray OP with the following property. Construct a point P dash on the ray OP, okay, with the property such that OP dash into OP is the radius k square. I mean, k is the radius of the circle. Okay, so this point P dash that we have constructed is called the inverse of P. Okay, this point P dash is called the inverse of P with respect to the circle CO comma K. Okay, so you compute the inverse of a point P with respect to a circle. This is the definition. Okay, now we instantly see a few cool properties of this definition. Okay, but before that, let's just actually try to pick a point P and execute this construction. So what you do is you pick a point P and you now join O to P. Okay, once you get the ray, you mark a point P dash such that OP into OP dash is equal to k square. Okay, so this point P dash is called the inverse of P. Now you immediately see a few cool properties. Okay, first property is that if P is dash is inverse of P, then because of the symmetry, OP into OP dash is k square, then OP dash into OP is also k square. So if P dash is inverse of P, then P is inverse of P dash. Okay, so P and P dashes are inverses of each other. The second thing you notice, by the way, this also means that the transformation which transforms all the points in the plane from P to P dash is an involution. Okay, this also is a statement that the inversion transformation, okay, as a transformation is an involution. Okay, all right. So what is the next thing? First, this next thing we notice that if OP is less than the radius k, notice that OP dash is bigger than k. Okay, first of all, let's note the easy case. If OP is equal to k, then OP dash also equals k. So if the point P is on the circle, P dash must be also on the circle, which means that P must equal P dash. Okay, so basically points on the circle remain fixed under involution. Those points don't move. Okay, so one thing we note is 2 points on the circle, points on CO comma K the circle of inversion don't move under inversion. They remain fixed. Okay, basically all I'm saying is P dash is equal to P if P is on the circle of inversion. On the other hand, points inside, okay, the circle, meaning in the disk here, the disk that is enclosed by the circle, if you take any point in the disk, all those points move out, because notice, if OP is less than K, meaning point P is inside the circle, then OP would be less than K. If the product is such that it's equal to K square and OP is less than K, OP dash must be bigger than K, which means P dash must be outside the circle, outside the disk. Okay. Conversely, if any point P is outside the disk, then OP is bigger than K, and then the inverse will be in fact inside the disk. So what happens is, under this transformation, all the points that are outside the disk get exchanged with the points which are inside the disk. Okay, points inside the disk are exchanged with points outside. Under inversion. Okay, under inversion, I didn't write under inversion, but under inversion this happens. Points inside the disk are exchanged with points outside the disk. Okay, all right. So these are two basic facts, and of course points on the circle don't move. Another fact to note, which is a very useful fact, is that if you pick any line passing through origin, okay, if you pick any line passing through origin, notice that under inversion this line doesn't move. Okay, this line doesn't move. So let L be a line. Let L be a line through the center of inversion to O. Then under inversion of the circle, the line is fixed. The reason is, notice that the points of the line are not necessarily fixed, but the line as a whole is fixed. What I mean by that is, because of this definition of OP into OP dash is R square, we choose P dash to be on the ray OP. We see that the inverse of any point P lies on the line OP. So which means, if you try to invert any point, okay, if you take any line L passing through O and if you pick any point P on it, then if the inverse of it is again on the line, okay, which means that all the points of the line go back to points on the line. Okay, therefore if you take any line passing through the origin, you can show that if you try to invert this line, it goes back to the same line. Now you have to be careful. I'm not saying every point on the line remains fixed. The points will move across, but the line as a whole remains fixed. That's what I'm saying. Okay, so these are the basic properties. Next we will see a cool property associated to inversion and a cool relation between inversion and orthogonal circles. See you next.